HEC just released HEC-RAS 7.0, and it comes with some solid updates for 2D bridge modeling. Let's take a look at the two modeling approaches available in 2D, then walk through the detailed methodology step by step. HEC-RAS 6.7 Beta introduced the two-layer 2D horizontal approach for detailed bridge modeling, including pressure flow and overtopping in 2D flow areas. Earlier versions mainly used a simplified 1D rating curve approach in 2D, which was suitable for overall bridge losses but did not offer the same level of detail for velocity mapping, complex bridge behavior, or scour assessment. Let's get started here. Step 1. Let's set up the basic geometry and run the model once to make sure everything is working as expected before adding the bridge details. First, let's open RAS version 7.0 and create a new project. Then open the geometric data editor and create a new geometry file. We will start the geometry there and later build on it in RAS Mapper. Once you are in RAS Mapper, the first thing to do is set the projection by browsing to your .prj file. After that, let's create a new terrain for a small study area to keep the model simple and easier to work with. Now let's go into Geometry Edit mode and create the 2D mesh using the existing perimeter and break line setup. At this stage, the goal is to make sure the mesh is clean, free of errors, and ready to run. Once the mesh is complete, draw the downstream boundary condition line and assign it as a normal depth boundary. After that, exit Edit mode and save the setup. Next, let's set up the unsteady flow file. Create a new flow file and name it Hypothetical Rainfall Event. Since we are applying rainfall directly over the 2D mesh, this will be a rain-on-mesh model. For this example, we will use normal depth as the downstream boundary condition. We can measure the boundary slope directly in RAS Mapper and then use that value in the flow editor. The final step is setting up the plan. Since this is a 6-hour storm, a 24-hour simulation window should be enough. At this stage, we are simply checking that the model runs cleanly without any issues, which is the main goal for now. A good modeling practice is to begin with a simple setup and add complexity incrementally, which makes troubleshooting much easier later on. As you can see, the model ran without any issues, which is a good starting point. Let's quickly review the results by checking the results folder and plotting the flow hydrograph at the outlet using a profile line. Everything looks good so far, so we are ready to move on and add the bridge details next. Now let's set up the bridge geometry using the Simplified method, also known as the family of rating curves method. There are two ways to draw the bridge deck in HEC-RAS. You can do it in the geometric data editor or in RAS Mapper. For this demo, let's use RAS Mapper. Go to the SA 2D connection tool and draw the bridge from left to right while looking downstream. Once the line is drawn, RAS will ask for the name, width, and structure type. Here, make sure to select the Simplified method from the structure type dropdown. Next, enforce the SA 2D connection as a break line so the cells align properly along the structure and help prevent leakage through the mesh. Once the cells are reinforced, save the geometry and exit RAS Mapper. Now let's open the geometric data editor. If you are already familiar with 1D bridges, the simplified 2D bridge setup will feel very similar. At this stage, we need to enter the deck details. Just like in 1D, the simplified 2D bridge method uses 4 bounding cross-sections to compute the bridge hydraulics. In 2D, the spacing of those cross-sections is controlled by the distance you enter in the deck editor, so that value plays an important role in how the bridge is represented. Now we need to prepare the bridge deck profile. In a real project, this information would usually come from built drawings, survey data, or bridge design plans. Since we do not have those for this demo, we will use RAS Mapper to build a reasonable deck profile from the data we already have. We can start by opening the profile plot along the SA2D centerline in HEC-RAS Mapper. Then we will copy that profile and paste it into Excel, where we can prepare and clean up the data. Excel makes it much easier to adjust elevations and define the bridge shape before entering it back into HEC-RAS. In practice, bridge details such as the bridge opening, pier locations, and deck elevations should come from actual bridge information. Those details are important because they directly control how the bridge is represented hydraulically. For this demo, we are going to simplify that process by making a few assumptions. Let's assume that the upstream bridge opening starts at station 68.14. From there, we will replace the relevant profile elevations with the known high chord elevations. Then across the bridge opening, we will also enter the known low chord elevations. This gives us the basic deck shape needed for the simplified bridge setup. Ideally, you would prepare separate deck profiles for the upstream and downstream bridge faces, since real bridges often vary from one side to the other. But for this demo, we will assume the same deck profile on both sides. That keeps the setup simple and lets us focus on the workflow itself. So the goal of this step is not to create a perfect surveyed bridge. The goal is to build a usable bridge deck profile from the available data, prepare it in Excel, and get it ready for entry into the bridge editor. All right, now, just like in 1D bridge modeling, we also need to define the pier details here. For this demo, we will keep it simple and use a single pier with a constant width of 1.5 feet at both the upstream and downstream sections. Once you enter the pier details and click OK, you should see the pier appear in the bridge layout. Similarly, you can also enter the abutment details here, but we will skip that part in this video. The next item is the bridge modeling approach. Depending on the flow condition and the level of submergence, you can choose either the energy method or the pressure ton-weir method. The energy method is generally used when the bridge opening is not submerged and the flow remains mostly open channel. The pressure-weir method is used when the bridge begins to submerge, pressure flow develops through the opening, or flow starts overtopping the deck. Another critical piece of information we need to enter here is the H-tab parameters. This is where we define the maximum headwater elevation and the maximum flow range that HEC-RAS should use when building the hydraulic tables for the bridge. In simple terms, these values help control how far the bridge curves are developed during pre-processing. It is a good idea to choose values that comfortably cover the range of flows and water surface elevations you expect, because the hydraulic tables usually come out better when both a reasonable maximum headwater elevation and a maximum flow are provided. The next step is to enter Manning's N values for all of the bounding cross-sections that are automatically formed by the user-entered bridge data. To enter Manning's N values for the 1D cross-sections, go to the Options menu and select External and Internal Bridge Cross-Sections. Next, we have Bridge Ineffective Regions. This option lets you define ineffective flow areas on the upstream and downstream cross-sections outside the bridge opening. If the left and right roadway approaches are included as part of the bridge, these ineffective areas may be needed so HEC-RAS can compute more accurate headwater and tailwater elevations for the bridge curves. At this point, the model is ready to run. We can use the existing plan from earlier, but let's rename it to Simplified Method so we can compare it with the detailed method later on. Let's see if it runs. All right, the plan ran without any model issues. Now let's go to HEC-RAS Mapper and turn on the results layer. From here, we can review the water surface elevation profile and later compare it with the detailed method. For better visualization, we can also turn on particle tracing to get a clearer picture of the flow paths and how water moves through the bridge area. With the simplified method complete, let's now move on to the detailed bridge modeling approach, also known as the pressure/overtopping method. Let's make a copy of the simplified bridge geometry we just worked on and modify that for the detailed method. Before we begin editing the geometry, let's also create a new plan so we can run the model as soon as the updates are done. Now let's return to edit mode for the copy geometry and update the bridge modeling approach in RAS Mapper. Other than that, the setup stays the same. Once the change is complete, save the geometry and close out of RAS Mapper. The next step is to place the piers directly into the terrain. This is a major difference in the detailed bridge method, because the pressure overtopping approach requires the piers and abutments to be included as part of the terrain itself. That allows RAS to better represent the flow behavior around the structure. To do that, open the pier editor and enter the top elevation, rotation angle, width, and the rest of the pier geometry. This part usually takes some engineering judgment and sometimes a bit of trial and error to get the pier aligned properly with the bridge and the flow path. If you have a built drawing or bridge report, that can make the positioning much more accurate. For this demo, we will use a single pier with the same dimensions as before. Once you are satisfied with the pier placement, save the terrain and exit. One tricky part of this method is that the pier placement needs to line up well with the cell faces and should not create leakage across the mesh. So the mesh around the pier has to be adjusted carefully. This is usually where break lines or local refinement regions become useful. HEC's bridge guidance recommends aligning the structure with cell faces. For this demo, I am going to use break lines and refine the mesh around the pier so the cells align properly. HEC-RAS 2025 beta version has emerged as a solid option for this refinement, as it has more advanced mesh control features. HEC does provide guidance on representing pier geometry within a HEC-RAS subgrid mesh, and that can be helpful when reviewing the mesh around the structure. Once the pier and surrounding cells look good to you, save the edits and close out of RAS Mapper. Now let's move into the Geometric Data Editor and open the Bridge Deck Editor. To keep things consistent between the two methods, we will use the same deck profile we used earlier. Note that the piers and abutments are already built into the terrain. Because of that, in the detailed method, the hydraulic computations are controlled by the terrain representation. So the pier and abutment details entered here do not govern the flow behavior around the structure. Lastly, we need to enter the bridge deck minor loss parameters and the deck Manning's roughness coefficient. These inputs are important because they affect how flow losses are represented across the bridge deck in the detailed method. And that's it. Let's run the new plan and see how the detailed method responds to the bridge hydraulics. Just keep in mind that this method is meant to be used with the shallow water equation solvers, since it is designed to resolve the bridge hydraulics in much more detail. All right, we are seeing the runtime message, removing cell, which is expected here since those cells are located within the piers. So that part looks fine. Now we can move on to the results and compare the two methods. Let's load the results and plot the water surface elevation profile. Here, the detailed method gives us slightly higher water surface elevation than the simplified method near the bridge. That is not surprising because the detailed method resolves the bridge hydraulics more directly, while the simplified method is mainly meant to capture the overall head loss. The trade-off is that the detailed method takes more setup effort and has more mesh sensitivity. It also comes with some built-in limitations. Key takeaway here is that use the simplified method when you want a stable and efficient bridge representation focused on overall losses, and use the detailed method when you need richer hydraulic detail, especially velocity distribution, pressure flow, or overtopping behavior at the bridge. And that's it for today. Please don't forget to like, share, and subscribe if you like the content.